Okay, so it should be recording. So I just wanted to quickly go over this question. If you took the 12 o'clock version, this is question number 1 from the 12 o'clock version. Most of the question ones for all the quizzes were the hardest, I believe, or like the trickiest. But the scores were pretty high for this quiz in general anyway. But yeah, so the first question says you're given this linear transformation and you want to know where A sends the basis vector V to. So if you want to know where A sends the basis vector V to, you just multiply by 1, 0. Right? So you multiply whatever this A is by 1, 0, and you get your answer. So that was mostly fine. Then part B said, describe the linear transformation, like what it does. So when it says describe the linear transformation, you should look at each separate matrix and see what each one does. Because remember, if we consider this like matrix B, matrix C, matrix D, the order of the transformation goes from right to left. So it goes B, then C, then D. What is B doing? Well, it sent 1, 0 to 0, -1. And it sent 0, 1 to 1, 0. So if you think about the like graph, it sent 1, 0. Now it's at 0, 1. So now it's here. And then it sent 0, 1, the J vector, to 1, 0. So now it's here. So it rotated 90 degrees clockwise. Then the second matrix here with 2, 0 and 0, -1/2, we see that it's just rescaling, right? Because it rescaled the x by 2, so it extended it. So it extended it over 2, and then it compressed the y-axis. Now it's here. Then the last one to the left, we see it brought 0, 1, or it brought the, so thinking about, not thinking of it, thinking separately, it brought 1, 0 to 0, 1, and it brought 0, 1, -1, 0. So in general, what is that? Well, you brought the I vector to here, and you brought the J vector to here. So you rotated 90 degrees counterclockwise. So overall, the transformations were that you rotate 90 degrees clockwise first, we rescaled the x and y axis, and then we rotated back counterclockwise. So what would that give you if you started with this smiley face here? We see that you would turn the smiley face clockwise, right? And then turn the smiley face clockwise, so we have like the circle and the square eye here. Yeah. Then we stretched it, and then we rotate it back. So then you get this final smiley face sign. Does anyone have any questions on that? Yeah.
Does the fact that it was like -1/2 change anything?
-1/2. Yes, it flipped it. So wait. Rescale by. Oh, sorry, no. It didn't flip it. The -1/2 means that. Oh wait. -1/2. Wait, you would turn it this way, stretch it. Wait, where does, if you had 2, 0, -1/2. Oh, I need to. It would say 0, 1. Negative. I feel like you're right, but
that's why it flips the eyes, like the eyes.
Oh, Yeah, sorry, thank you. The eyes are flipped this way because okay, if we turned it clockwise first, then we rotate it clockwise. So now the eyes are like here, square here, and the circle here. So that was rotating it. Yeah. Then you expand it, stretch it by 2. So now it's this way. Stretch it by 2 on the x-axis, and on the y it flips. So when the eyes flip, so circle square. And then finally you rotate it back counterclockwise. So now we have this on the square circle. Any other questions on that? Okay, so let's get into this week's material then. So just quick definitions. I'm just gonna skim through. You don't have to copy this down, but just like a terminology. So the zero matrix, we know, has all zeros in the matrix. Identity matrix, ones across the diagonal. If you have a linear function like ax plus b, where a is some constant matrix, then our derivative matrix will just be all of those constants from your matrix A. So it'll be like A11 all the way down to AM1. Essentially, it gives you back the matrix A. And you can think about it because you're taking the derivative of with respect to x. So if you were taking the derivative normally, what would this give you? It'd give you f prime of x equals A. So yeah. Okay, then we have derivatives with respect to linear combinations. So derivatives follow linearity, right? So if you're adding the derivative of two functions, f plus g, you can separate those and just do the derivative of the first function plus the derivative of the second function. It also works for the constant multiple rule. You can take out constants. And the same for product rule. So you may have noticed the rules with what is the derivative of a dot product or what is the derivative of a cross product. You can also use these rules. And finally, Bryce mentioned a nice trick in the video. If you write your function as like x transpose, this capital T is transpose ax, then its derivative, you can use this nice formula trick. Okay, then we go into the chain rule. So those are all like the fundamental rules. And now the chain rule is one of the biggest rules, right? So the derivative of f of g of x, we notice that it'll be the derivative of f times the derivative of g. And if you want to find it at a specific point A, then note the formula here. Notice that here we put an A, here there's a g of A, and here there's another A. So you want to pay attention to your values that you're evaluating your derivative at, because these highlighted ones are very important to pay attention to. There's also another notation that says the same exact thing, just with like partial derivative, like symbols instead. And that's this formula. It's saying the same exact thing as this capital D formula, just with different notation. Any questions on what I've said up to date? Yes.
If you have like 3 functions that are 2 units combined, and the intercept.
Yes. Yes. You mean like the matrix has one element?
Yeah, it's like they only ask you for the DF. Only one element.
Like this. This wait, this element. Or no, still this.
Like that matrix, does that have like 3 different elements? But like you only need to find one of
Oh yeah, you don't have to find the whole thing.
So we don't use a matrix for something like that.
Yes. So yes, if they were just asking you to find like one partial of your matrix, you don't have to actually do out the whole work. And that's where the classical chain rule comes into handy. So using this formula with the derivatives, the matrices for the chain rule, you would actually have to multiply out your matrix, right, to get your final answer. But say like Beatrice just said, sorry, I'm like, don't remember names. Okay, just like Beatrice said, if you wanted to find just a single partial derivative, you don't want to do all that work. You could just use the classical chain rule, which says that if you just want to find one partial, so say you have a function g, where x is g of t, and you have another function f, where w is f of x. This is the formula for it. You basically want to see what are the inputs and outputs. So if we wanted to find partial of w with respect to some t, so notice that we're starting at like here, w with respect to t, but t is over here with x. So what's in between, like what's stuck in between the w and the t? Well, it's the x. So that's why we have a partial x, partial x. And then depending on what x how many outputs x has, you might need to do even more partials. So this is just a formula, but I'll do an example right now. Okay. So here's a question. If you had w equals this, x squared plus y squared, y equals r minus s, or sorry, x equals r minus s, y equals r plus s. And you wanted to find the partial of w with respect to r, then what could you do? Well, we notice that w is in terms of x and y. X and y are in terms of r and s's. So the first method that you could do is, say we're unsure, we didn't know about the classical chain rule. We just multiply everything out and find the answer. So if we wanted to use the chain rule says we do partial of this, or derivative of f of g, that equals the derivative of f times the derivative of g. Now, what are the components of f? Or what is the size of our matrix for f? Yes. Yes, 1 by 2. 1 by 2. And our elements should be, well, f, right now we're defining it as w. So this is our output. And our inputs are x and y. So we do the partial of w with respect to x and the partial of w with respect to y. Then for the derivative of g, this should be how many outputs are there? There's an x and a y, so there's 2 outputs. There's an r and an s, so 2 inputs. So this should be a 2 by 2 matrix where our first output we consider at x, so we do partial of x, but our inputs, there are and s. Then the second row is your second output, and your inputs are r and s again. So just in terms of formulas, let me show you what this becomes. So if you were to multiply out like a matrix, you get partial of wx with partial r plus these 2 terms. So partial of w with c, y of r. And then for your second row, you get partial of this times now the second column plus wy times this. Just in terms of elements, not computing any numbers yet. Now, what exactly is the partial of, so let me put that in like a smaller step. What is the partial of W with respect to X for our first term? It's just 2x, right? What is the partial of W with respect to Y? Well, the derivative of this is 2y. So we put a 2y. Then the partial of X with respect to R. So X is our first output. Take the derivative with respect to R, we get 1. Derivative with respect to X is -1. Then our second output in red, partial with respect to R is 1, with respect to S is 1. So when you multiply this, you get 2x plus 2y and -2x plus 2y. So I don't want to stop there because our answer right now is in terms of x's and y's. But what was our original question? We wanted things in terms of an r or an s. So we have to take what were x and y. X was, so let me copy this here. X was r minus s. So let's plug that in. R minus s plus 2. Y was r plus s. That's our first term. Then over here, we do the same thing and we plug in what were x and y. And so if you simplify that, you get 4r and 4s. Any questions on that process? Yeah.
Was the stuff in purple, was that just to kind of show what it was? You weren't really using that to come to the final answer?
Yeah. Yep, I was just showing what it was. Okay. And why I showed that is because this is our first method. We multiplied everything out, and our answer would be that this 4r is our partial of w with respect to r, and this is partial of w with respect to s. That was what our question was asking us. But you could have done it a second way, method 2, by using the classical chain rule, which says that the partial with respect to r will be what are the different in so w, what are the different inputs of w, x and y? So we need to take those two inputs into consideration. So we need a w with respect to x, and we're gonna have a w with respect to y. Then looking at x was in terms of r and s. So we can take the partial of x with respect to r. And notice how you can imagine like this canceling out, I guess, and you have a partial of w with respect to r. Plus, you'd want to do the same thing with y. And notice that this line is the same as the first purple row I wrote earlier. So you could have done it the purple way or the classical chain row way, like just the formula, or you could have like multiplied everything out. So if you follow our formula here though, you notice that you will get the same exact answer. So you get 2x plus 2y. And then again, you plug in what was s and what was y. And you get the same answer of 4r. And you can do the same thing with the partial with respect to s. And you should get the same exact answer. So either way works. Any questions? Okay, next question then. So this is from recitation question 59. So if you're given the partial or the derivative of f of g and the derivative of g, and you want to find the derivative of f. So without doing numbers yet, what should I do in order to find the partial derivative of f? Like, what do we know about matrices that we could do to get this alone? Yes. Yes. So if we multiplied both sides by the derivative, the inverse of the derivative of g of a, okay, inverse, then we'll get that our derivative of f of g times d of g inverse equals df at g of a, which is what we want. And so at this point, it's just numbers. So I'll let you guys do that on your own. The answer will be this matrix. Just wanted to introduce the concept of that. Any questions on that? Okay. Next we have inverse function theorem. So in single variable calculus, we learned this. Right? If you wanted to do the derivative of the inverse, you could just first find the derivative and then take that inverse. Like that was the trick in single variable calculus. Or in other words, if you did this term multiplied by this, you should get 1. They're inverses of each other. So now it's the same thing, but now we're in higher dimensions. So we need these derivative matrices. So similarly, the derivative of the inverse is the same as if you first do the derivative, then take the inverse. So this green thing is our formula. And if you specifically want it at a point, then notice that on the left here, you should have f of a as your point of evaluation. But over here, you should have a as your point of evaluation. And why does it say like f is locally invertible near f of a? It's because notice that if you start at a point a and your function takes it to your y value, your f of a over here. Well, there might be multiple different inverses taking things back. So we just want to guarantee that in some area near f of a, some inverse is going to exist so that we can get back to a. And we need that because our f took us from xy to f of xy, right? So by definition, the inverse should take f of xy back to xy. That makes sense. That's single variable calculus. Now we're dealing with derivatives. So naturally, if our inverse takes us from f of xy to xy, our derivative of the inverse should also take us from xy, f of xy back to xy. We also know that the derivative of f should take us from xy to f of xy. So let me make this in purple. And so if df takes us from here to here, well, the inverse of df should go backwards. So we notice what was the point of this? Just saying that the two purple terms, they're the same formula. So they are equal to each other. If you think about like f and their inverse. Any questions on the definition? Yeah. Yes. So, well, let me do an example to clarify that. We'll see why. Okay, so let me do, okay, since you said that, let me skip to the important example. Okay. Whoops. Okay. Okay, let me do this. Okay, so if we assume that our function f is like x squared, then our inverse is square root of x, right? So if we follow the formula like this, and we're specifically doing it at a point x equals 2, well, then following the purple, the left-hand side, we just plug in. So f inverse of derivative of f of 2. What is f of 2? We plug in here, it's 4. Then what is the derivative of our inverse? Well, our inverse is x to the 1/2. So the derivative of x to the 1/2 is 1/2 x to the negative 1/2. And we're evaluating that at 4. We get 1/4. That's fine. Let's try the orange way. The orange way says we do the derivative of the inverse plugged in at 2. So what is the derivative of f? Well, that's 2x. And we want to take its inverse. So the inverse of 2x, if you do it, so usually to take the inverse, we switch the x's and y's, and we solve for y. So y is 1/2 x, and we plug it in 2, we get 1/4. Same exact answer. We saw that the formula worked, specifically where the orange is plugged in at a, and the purple is at f of a. However, I have a question. So do you guys think this statement should be true or not? If you think it's true, raise your hand. If you think it's false, raise your hand. Okay, a few more falses. Yeah, so this is false, not true. And we can see why. So this is why your points of evaluation matter. Using our last example, so f of x equals x squared and our x equals 2, right? We can try to see if this works. So d at f inverse of a times df at a. So what is our inverse? Well, we should be doing the derivative of, so our inverse is square root x, right? Because if we switch x's and y's here, we get y equals square root x. So that's our inverse. And we're evaluating that at x equals 2. Towards our evaluation point. The derivative of f, that's just 2x. Evaluated at x equals 2 again. Then what is the derivative of square root x? That's 1/2 x to the negative 1/2 at x equals 2. If you plug in 2 here, you get 4. 2 times 2 is 4. What about if you plug in 2 here? You get 1/2 square root 2 times 4. But this is not 1. So we got how if we plug in x equals 2 for both, we don't get 1. We don't get that they're inverses. So that's why we need this term, this d of f inverse, to be evaluated at f of a, not just a. Any questions on that? Another reason why it works is that we know that the derivative of your composition should equal I, right? Because from single variable calculus, we know that f of f inverse x should equal x, and f inverse of f of x should equal x, right? So now we're just dealing with matrices instead. So we're setting it equal to I. Simplifying this gives d of f inverse at f of a, df a. Why? Because f, if you start with f, it takes your point a, then it goes, so f, yeah, f takes a to f of a. Then you take that output and you put it into f inverse. So you take that output of a and you bring it back to a. So that's why the point we're evaluating at for your derivative inverse matrix we start at f of a, so that's why you're plugging in f of a here. And then you get out a. Okay, and since that equals this equals the identity, if we took the inverse of both sides, we get our exact formula for the inverse formula, inverse here, inverse. And this is how we got our formula for why both of these are equal. Any questions on that? Okay, let's consider a tricky example. So if we take our point, so this is from discussion problems. Let's take a point 0, 0. There could be a situation where we're given the derivative of f of g, we're given the derivative of f, but we might not be able to find the derivative of g. Can anyone think of a reason why we might not be able to find d of g in some cases? Like, what is the condition where, yeah.
That formal definition of the limit. So let's insert special case.
Yes, and what does it not fulfilling the limit mean?
It means that it doesn't equal the graph.
Yeah, so okay, so that works. You could also say that if it doesn't fulfill your limit definition, that means that we can't find our inverse. So if the inverse is, oh wait, sorry, f, should be f, is not invertible, then we won't be able to find the derivative of g, right? Because how we find the derivative of g is that we need to multiply by the inverse of the derivative of f. If we can't even find the inverse of this, how can we find the derivative of g? Okay, next situation. What about where your derivative of f of g and the derivative of f exist? Like you can actually find it, but then it turns out that this derivative itself doesn't exist. So the previous situation was just where, given our information, given certain information, we weren't able to physically calculate dg. But here it's where, like, you actually can't, like, it actually doesn't exist. So let me give an example. If you had a function g in terms of u and v, where it equals the absolute value of u and 0, and you had f of xy equals x squared 0. Well, then what would the composition of f of g be? You can, so just like how we deal with normal functions, you take the output of g of f, g of uv, which is this highlighted part, and we plug that into f. So if we plug this into f, we would get absolute value u squared and 0. So this is u squared 0. Then if you take the derivative of this composition at 0, 0, we get 2u 0, 0, 0. And evaluated at that point, we get the 0 matrix. So that's fine, the composition exists. We can also find the derivative of f, and we see that it also exists. And it's still the 0 matrix. That works out. However, if you try to compute the derivative of g, then we get the partial of absolute value u, 0, 0, 0. But what is the partial of the absolute value of u at 0, 0? Doesn't exist, correct. Doesn't exist. The derivative doesn't exist. So dg itself actually does not exist. So here we saw an example where the derivative of the composition and the derivative of f existed, but the derivative of g didn't exist for some reason. Okay, any questions on that?
Is this something where the case is so limited that it's not really worth checking? Or is this very much a special case, or should we, or there are checks we should do to make sure that the derivative partial matrix partial derivative exists before we use this?
I would say on the quiz, this might not, like, this is like a very like niche example, I guess. On the quiz, it might be like a nicer example where it will exist, like everything will exist. Yeah.
So what are the implications of that? Does that mean that like our composition, like our combination of the derivatives is valid, or it's just like it's within?
It's the derivative of the composition still works. It's just that you can't find the derivative of g. Okay, any other questions? Okay, let's do implicit function theorem. So for the, I think on the study guide, they said you don't need to know it. Perhaps. Would anyone like to see implicit function theorem or continue doing inverse rule stuff? Raise your hand for yes, implicit function theorem. Okay, there's 2 votes. All right, I guess, or raise your hand if you don't want to do it and want to keep doing more problems with the other. Oh, okay, sorry, majority, I think majority will rule in this case. You can still check out my notes though, they are posted. Okay, so let's keep doing. Oh, I wrote the answer here, but, oh, let's do this example, okay. If we want to, so this is recitation question 65. So we want to compute the inverse of this at W of 1, 2. Okay, so what should be the first thing we check before you even calculate this? Like, if you were given a function f or a matrix, you were given a matrix and you want to find its inverse. What should we, yeah. Yes, correct. And so checking if it's invertible means that the determinant of our derivative at the point should not equal 0. So first thing we always check first, is it even invertible at all? So right now we're given our function, which is this. And so what should our df? We should take our first output, which is highlighted in yellow. We take the derivative with respect to u. So that should give us 3v. Then the derivative with respect to v is 3u plus 2v. Then we take the second output in green. Derivative with respect to u should be 2uv. Respect to v should be u squared. Now, if we want to evaluate it at our point, which is 1, 2, and you plug it in, you get that it's 6, 4, 7, and 1. Thus, the determinant is 6 minus 28, or negative 22. So it's not 0. Nice. Okay, step 2. Now that we know it's invertible, we can use our inverse function theorem to find the derivative of the inverse more easily. So what is the derivative of the inverse? According to our formula, it's our derivative, then you take the inverse. Special note to these input values here. So now, well, we already found what is the derivative of f, right? We just found it in yellow. So let's put that in. It was oh, not in that yellow, this yellow. So you get 3v, 2uv, 3u plus 2v, u squared inverse. And so just using the variables themselves, you could find that this is your determinant, and you find the inverse matrix. Just using the variables themselves. Or instead of like using the variables, you could have just used the numbers, but I just did it both to show you guys. So you could have just taken the green and directly found it. Or if you wanted to use the variables, keep doing it the orange way and you get the same answer. So this is the derivative of our inverse. Any questions on how I got that? Okay. The next question is related to this still. So it says, write an expression that is satisfied by the set of points for which the function w above is not invertible. So what do you guys think should be the expression that we use to determine if it's invertible or not? Yes.
Oh, it is.
Or is not.
0, 0.
As our expression.
Oh, right. Oh, not what you should put in.
Mhm. Yes. Yeah. So by the inverse function theorem, it's only invertible near f if we want our derivative to be invertible. Right? And being invertible means that we want our determinant to not be 0. And if you find the determinant, that's why I use the variables above in the orange. The determinant in terms of variables is this. So this would be our expression to make sure, or like if this equals 0, then our function would not be invertible. But if it's not equal to 0, then it is invertible. Any questions on that? Okay, let's see. Okay, so we did, let me see if there's any other. Okay, let's just do a quick implicit function theorem since we already did an extra example. So if you're given some capital F function in terms of x and y, we want to rewrite it first so that it equals some expression, meaning equals some expression equals 0. Now f, if we say that we have m equations and x has n variables, y has m variables, then we can express y near a point so that it satisfies our function evaluated at a. But that only happens when the determinant is not 0. So we've noticed a trend that we keep needing things to be invertible for things to work out nicely. And this is our equation for the implicit function theorem. Okay, but the definition is kind of confusing, so let's do an example that makes more sense. So if we want to show that near some point, 1, 1, 1, 1, we can solve these two equations uniquely for u and v as functions of x and y. So we want to show that we can solve it, then actually use the implicit function theorem to find this expression. So what does this mean? When it says to solve uniquely for something, we want to call that something or y. So I wrote like little quotations y. And as functions of something else means that any other variables, let's just call that x. So step 1. First, we want to make the implicit function theorem. Meaning, let's restate what was. So we're given these two equations. The yellow one is our first output, And then the green one is our second output. So we can rewrite our function as, let's write the first output, -2, because I want to bring it over so that I have something equal 0. Then our second output is this, the second one, -2 again. And we know that that equals 0, 0, because we just solved for those two equations. Let me call the first output like P and the second one Q. So first step, we wrote our function. Second step, identify Y and X. So I just said above, Y is what we're looking for. So let's call it U and V. And let's call X everything else. Well, we took care of U and V. So the only variables of inputs that are left are X and Y. Okay, third step, if the determinant is non-zero, we want to use our equation. So let's find our determinant. So let me move this closer here. So what is the partial of F with respect to Y? Well, F right now we have two inputs, Y is UV, so two inputs and two outputs. So we take the partial of, I called it P with respect to U and with respect to V. And on the second output, I called it Q, right? And with respect to those same inputs. So when you take the derivative, that would give you X plus 2YV, 3U squared X, YU squared, and 4Y squared V cubed. And all along, we're evaluating it at our point 1, 1, 1, 1. So if you plug these in, you get this matrix. The determinant is 12 minus 3 or 9. Not 0, which is good for us. So we can use our equation. Okay, so now using our equation, let's first, we already found this. Oh wait, we did not find it. We found this without the inverse, so that's that. So let's find the first thing we need. In purple, partial of F with respect to Y inverse at our point 1, 1, 1, 1 is you can just take the inverse of what we just found, this 3, 1, 3, 4 thing, which is 1, 9, 4, -3, -1, 3. Now we need this part, partial of F with respect to X. So what is our F? Our F had two outputs. Okay, this is getting slightly small, so let me paste it down here. Our F has two outputs. X, we called X as XY. So that's two inputs. So we should have a 2 by 2 matrix. Specifically, it should be our first input again, with respect to our two inputs, our second output with respect to our other inputs again. And so you can evaluate that and you get U cubed, VU squared, 2YV to the fourth. And remember, we're evaluating this at our input or our point of evaluation, which is 1, 1, 1, 1, or gives you this red matrix here. So now that we have our two components, we can use our formula up here. So let me plug in our formula. So we have this as our equation. The first thing we found in purple, don't forget the negative sign. And then times the red thing, which is 1, 1, 1, 2. Or you get wait, negative 193023. Oh, any questions on how I got on that question? Okay, if not, then yeah, recitation is over. Thanks, guys. Recording.